Chapter 3, Network Protocols and Communications. Hang in there on this chapter. This one may get a bit confusing, but this is the foundations for networking from here on out. So hang on for the ride. If you go into your module and you click Launch Chapter 3.4, then click Launch Content, it brings you to the e-book information. I suggest that you use this even if you have a book. There's a lot of different tutorials through here and examples to help you understand the material just a little bit better. What we're going to do in this unit is we're going to try to explain why protocols are necessary in communication, explain the purpose of adhering to the protocol suite. You need to be able to explain the role of standard organizations in establishing protocols for network interoperability. That just means so that your networks can talk to each other. We're going to explain how the TCP/IP model and the OSI model are used to facilitate standardization in the communication process. We're going to explain why RFCs become the process for establishing standards. We're going to describe the RFC process. We're going to explain how data encapsulation allows data to be transported across the network. We're also going to explain how local hosts access local resources on the network, and also how they access remote resources on a network. Just so that you know, there are standards in place. There's network protocols and standards that make the networks easier to communicate with each other. They were set up so that everybody is on the same page, basically so that everybody is following the same game plan. There are certain rules for communication that needs to be followed, and that's true with personal conversations that you have with each other face to face. It also goes with when you have communication between device and device. If you're using the e-resources, you can watch this short demonstration that it shows you how humans communicate. We have our message source, who's the first person talking. They have their signal, and it's transmitted over medium. Then the signal is received by the receiver or the person they're talking to, and that reaches their destination. So here's a little example of that. Then we have computer communication. You have your message source, you have your signal, you have your transmission medium, you have your signal receiver, and then where the message is received. So here we have the information that comes from this laptop, crosses the medium, and then it comes to this desktop. That's how the computer also communicated, very similar to how a person communicates. When we communicate with other people, there's several parts of our communication that we typically follow, or the rules. There's an identified sender and a receiver. If you're the one speaking, you are the sender. The person listening is the receiver. There's a common language and grammar. And the speed and timing of delivery is important. Then you have confirmation or acknowledgement is also required. You want to know that the person heard you. An example here is, here's some human communication that governs rules. Basically, you can't understand what these sentences here say. Nothing is in any particular order. But if we translate those, it puts the words and the letters in the order that they're intended to be in, and it makes more sense. The same is true for computers. We need certain protocols or communication standards for us to follow. So we have message encoding, we have message formatting and encapsulation, Our messages can be a certain size. If they're larger than is intended, then it's broken up into smaller portions so that the message can be sent. You have message timing and you have message delivery options. Message encoding for people. She has the information. She's telling him what she sees or what she's thinking of. He translates that information. For the computer, it works in very similar ways. The computer has its source encoded. It sends out its packet of information. The destination computer receives it and decodes that information in order to understand what is going on with this device or with this message. When a message is sent from the source to its destination, all the information contained in that message must be in a specific format or specific structure. This is true in human communications. It's also true with devices when they communicate. An example here is a letter that has been written. There are certain things that we have to have. We have to be able to identify the recipient. You have a salutations or greeting, the message content, the closing phrase, and an identifier of the sender. So here's an example. Information, you have Dear Jane, you have the body, you have who it's from. That is the recipient's information. Who are you sending it to? You have the sender's information or the source. You have the dear, which indicates that's where this letter began, who it's to. Then you have the content of the letter, and that's encapsulated data. And then you have the sender source identifier. And on a mail that you send through snail mail, you'd also have postage, and that indicates that that's the end of that letter. So we have our destination and our source. Both are physical and hardware addresses. That's your frame addressing. That's like on the outside of your envelope. You have your start flag, and that's the start of the message indicator. This is our encapsulated message. This is what's encapsulated together. You have your recipient destination identifier so that it knows where it's going. Your source identifier so that you can signal who it came from. And then you have your data that is encapsulated into bits within that. One thing to keep in mind when you're sending information electronically or between devices is that the format and contents of a frame are determined by the type of message being sent and the channel over which it's being sent or communicated. Messages that are not correctly formatted are not successfully delivered to a process by the destination host. If it doesn't get all of its if it does not receive all the pieces that it needs for the communication, then it can't reassemble the information in a logical order. As I mentioned earlier, the message size is important. And if the message is too large, your computer is going to break that package down for you into reasonable sizes. The size restriction of frames require that the source host to break a long message into individual pieces that meet both the minimum and maximum size requirements. This is known as segmenting. And each segment is encapsulated in a separate frame with the address information and is sent over the network. At the receiving host, the messages are de-encapsulated and put back together to be processed and interpreted. And this decapsulation, it puts them back together in the correct order that they need to go in. We have message timing. That's important. In what order do you receive the information? If you were speaking with someone and they couldn't understand you, or you are both talking over each other, that makes your conversation difficult. There's several things to look at. We have our access method, and that determines when someone is able to send a message. And these timing rules are based on the environment. For example, you may be able to speak whenever you have something to say. In this environment, a person must wait until no one else is talking before speaking. If two people speak at the same time, a collision of information occurs, and it's necessary for the two to back off and start again. And if you have to back up and start again, you typically wait a second or 2 seconds in order to see if the other person is going to start speaking again. The same thing is true with your segments and the packets that you're sending. With flow control, timings also affects how much information can be sent and the speed that it can be delivered. If one person speaks too quickly, it's difficult for the other person to hear and understand. With our network communication, a sending host can transmit messages at a faster rate than the destination host can receive this and process it. So if it's getting the information too quickly, it's liable to drop packets, and then when it starts to put them back together again, it doesn't have all the pieces that it needs. We can have response timeouts, and when people do this, they ask a question. If they don't get an answer back, then they're going to ask it again. When we're talking about networks, there are also rules that apply here. The hosts on the network specify how long to wait for responses and what action to take if the response times out. So if I say you can send this out for 3 milliseconds before I hear a response, if I don't hear anything, I may drop it, or I may try resending it. It depends on what the host needs to do, how it's been configured. When we communicate, we may communicate using different types or patterns of delivering our information. We may speak to one person, we may speak to several people, or we may be speaking to a group. And the host on the network use similar information. An example here for unicast is if this lady was talking only to this gentleman, that would be unicast. Multicast, she's speaking, but only to 2 of these 4. And broadcast, the message is being sent out to everyone. The same works on the computer system. We have our unicast. When we send out a message from the source, it goes directly to its intended recipient. Multicast, it may go out to several recipients. And then a broadcast message is going to go to all the devices that's on your system. Besides the different methods of sending out the message, one thing you need to keep in mind is that hosts have requirements for acknowledged versus unacknowledged messages. So it depends on whether or not they've heard back from the recipients or not. If they've heard back, that is acknowledged. If they hear nothing back, that is unacknowledged message.